study by Marco Gualtieri in his PhD thesis in 2004. I don't expect you guys to know what they are yet. I'll spend a whole bunch of slides talking about them. I'll spend these many slides talking about them. Okay, so that's when it's like, what? So many slides. So it's going to be a long time just talking about generalized complex structures. But for now, I'd like just to give a few kind of key things that you could take home with you anyway. One of them is that they unify complex and symplectic structures, which means, oh, look at that, Rafael Torres. Hello, Rafael. So they unify complex and symplectic structures, which means just that complex structures are an example of transcomplex structures, and symplectic also are an example. You can think of, there are other things that happen like that. If you have taken a course in symplectic geometry, there is the isotropic manifolds, which are simultaneous generalizations of Lagrangians, and the total space, which is symplectic manifold. So you could think of that kind of thing. Like it could also be something that you'd like to keep in mind. Like, what kind of generalization is this? What do I get extra? One feature that you get that isotropic picture doesn't really get is that you can actually deform. So there are some cases in which you can start with something which is, say, complex, and deforming the transcomplex world. You are integrable, you are good all the time, but you start complex and you end symplectic. So that's something that actually is possible, and we find an interesting feature. And even more interesting is the fact that, because in this first example is something that the manifold at each point, so like you're varying the structure, but at each point the structure is either fully complex, as you know it, or say fully symplectic, as you know it. So it's not something in between. And one thing that's interesting is that you can actually have complex and symplectic points on the same connected manifold as well. So that's a different feature. So in a manifold, symplectic and complex points can coexist. Okay. And this sequence of 5 bullet points is what I'm going to be talking about for all those slides over there. They are also related to a few other things, not just to the complex and symplectic, but that's kind of what got our attention going. But they're also related to real Poisson manifolds. That was something that Marius proved back in 2011. They're also related to holomorphic Poisson manifolds, and that's what I'm going to be talking mostly about today. So that is this other collection of slides here. All of them. So like, what's the connection to the holomorphic Poisson world? And the last one is just a hope that I have, which is that they would be useful to talk about Fano varieties, smooth Fano varieties, or at least a differential geometric generalization of that. So it should be something broader than Fanos, but hopefully they also include things that you'd like to say about Fano varieties from complex geometry, if you know what those are. They are not going to appear today, the Fano varieties, so I'm not going to develop on that one, but I'll mostly be talking about holomorphic Poisson later. And stuff that I won't talk about, but it's good just to give like an idea of what they're good for. Oh, he's still waiting in the lobby. Is he in now? Rafael, are you in?
Yes, yeah.
Okay, hey man. Good you're here. Anyway, so what I won't talk about, but it's just useful to know, because it's say like, oh no, like I'm interested in complex geometry, my neighbor is interested in symplectic geometry. Maybe I don't care about the other weird stuff that happens in the middle. And then it would be useful to know, like, did you introduce them for some other reason, or is it just because it's like a nice generalization that like is cute and nice to work with or something? And the point is that from the moment of the introduction, they kind of hit a few buttons with string theory. So there's this concept of generalized Keller manifolds, and they appear as solutions to the 2,2 supersymmetric sigma model. One interesting thing is that the supersymmetric sigma model, that one there, was already introduced back in '84, here at the bottom of the slide. And the generalized Keller notion only appeared in 2004. So in a way, the fact that the solutions were necessary and existed and had some weird geometric feature was already present, but people didn't know really how to grasp them. It was phrased in terms of bi-Hermitian geometry. So it required 2 complex structures compatible with the same metric and satisfying a differential equation together. It's something that people did not really have a way to put their hands on. So there was really no development in the theory of 2,2 supersymmetric sigma models for a long time. It was also proved that they are solutions to the topological A and B models. So typically one would ask for like a complex manifold with trivial canonical bundle, or symplectic manifold. The A is for symplectic and B is for complex, but the general solution to be generalized complex as well. One feature that appears that they give the mathematical framework for T-duality, and hopefully that's going to shed eventually some light into mirror symmetry, except that that remains a long path ahead. And more recently, in the work of Garcia Fernandez and other people, 2013, I don't know if you guys can see at the bottom there, because in the room it's difficult. So it was actually related, this whole Transcomplex framework, to heterotic strings. And in fact, only 2013 or so is when people finally formalized T-duality for heterotic strings, which is crazy because physicists always say the theory should be T-duality invariant. Heterotic strings are super old, but the whole way to formalize it is very recent. And in fact, there are a whole bunch of gaps in the knowledge there still. So there is actually research projects to be done in that area. Anyway, so this is what I'm going to do. So that's the outlook of the presentation, the outline. I'll be telling you a whole bunch about Transcomplex structures, trying to justify the claims I just made. Then after doing all of that, which is going to take a lot of slides, I'll talk about deformations and then local form theorems, which is essentially the aim of the talk. So the deformation local form theorems have to do with the Poisson thing, and that's really the aim that I would really like to get. The final message is that Transcomplex geometry is closely related to holomorphic Poisson structures. So I started with just a differentiable construction, and you can think like in differential geometry, you have partitions of unit and all sorts of nasty things. But in the end of the day, there is something complex analytic about Transcomplex manifolds that you will not be able to guess from the start. Okay. So where do they live? So that's the first question. So before I start talking about Transcomplex structures, I just have to talk about the space where they live. So they live on a manifold, so that's a given. But instead of putting something on the tangent space, which is where you would normally put things, like complex structure would be an automorphism of the tangent bundles, that's fine, squares minus identity. Or symplectic structure would be a non-degenerate two-form on the tangent bundle. So here it's something else. You have to look at the sum of tangent plus cotangent bundle, and that's where my stuff will live. Now, what happens is that in the sum of tangent plus cotangent, you have some data there. There are some objects you can deal with there, and some of them depend on more than just the manifold. So in this case, you actually need a closed real tree form as well. So every time you give me a closed real tree form, I can get some structure. You could think of it a bit like a connection on the tangent bundle. If you give me one and you want to get another one, you have to give me a one form if that is an endomorphism. So there is some sort of ambiguity here. Can you have more than one? So it depends on some choice you have to make ahead of time. In this case, the choice is a real closed tree form. And the structure that the sum of tangent plus cotangent has is this natural pairing, just because it's a sum of two, like a vector space plus its dual, so you can pair an element of the dual with an element of the vector space to get a number. So we always consider the symmetric pairing. Technically, you could say, oh, there's also a skew symmetric one. It's just that one doesn't appear very often, so I'm not going to introduce it. But that's a pointwise operation. If you have a vector and a form at a point, you can do that operation there. And there is something which is an extension of the Lie bracket, which is this expression here. It's called the Courant bracket or the Dorfman bracket or the Courant-Dorfman bracket. And you see that the tree-form H appears as one of the things here. So you have a bracket which starts with the Lie bracket, has a few extra terms which are one forms. So that has to do with the fact that if you have a psi or eta, you end up having a one form at the other end as well. But even if you did not have psi or eta, if you have an age, it also causes the presence of a one form appearing there. It's just something that's there, and it's natural to consider. I actually not pay attention that much to the existence of this tree form, and often it's going to be zero anyway. But it's just good to know that it's a natural thing in your theory. So I think originally we actually consider without the age, and that also goes fine. But even if you don't have the age, somehow it manifests itself every now and then. You kind of are reminded that it exists and is zero, which is different from not existing. And this bracket that you have there is related to this action of this operator, which is just taking the exterior derivative plus and then wedging with age. So whenever we start talking about bracket on things, often there is a translation of that into just how this d-age operator acts on forms. One interesting thing of T plus T star is that it has symmetries. So essentially symmetries are things which should preserve the pairing and the bracket, right? So you have these two structures, and if you have something to preserve those two, it's a symmetry, not just of the manifold underneath it, but also of T plus T star. And of course, diffeomorphisms are symmetries because the bracket was Lie bracket Lie derivative, so it's all diffeomorphism invariant. The pairing is also diffeomorphism invariant. There is this age. So if you do a diffeomorphism on age and pull it back, you kind of change age into the pullback of age. So technically, at that stage, you'd have diffeomorphisms which preserve a tree form, are symmetries, which is kind of weird. But these are symmetries. More interesting, but if age is 0, then every diffeomorphism is good, right? So originally we used to think of age as being 0. Two forms actually relate different brackets, and I didn't check, so there might be a sign mistake on that one. Might be age minus dB instead of age plus dB. I never check. But the point is that there is a relationship. So if you pick a 2 form, real 2 form, you can do this, and e to the b is just this thing. So I actually forgot to write. X plus psi gets mapped to x plus psi plus b of x. That's e to the b. Okay, so it sends elements of t plus t star into elements of t plus t star. Even if it was just a vector, it will become vector plus form. And when you do that, you change the age within its cohomology class. So add dB to it. So what you see is that if B was closed, then it would not have changed age at all. So closed forms are symmetries. But also, if you have a diffeomorphism that changes age within its cohomology class, then you can fix that by using a B. So the full symmetry is an extension of the diffeomorphism that preserved the cohomology class H by the closed 2 forms. And in particular, if you look at, say, the connected components of the identity, it's always identity cohomology. So you get that the connected components of the identity of the diffeomorphism group will be there in your symmetry of t plus t star. And in particular, sections of t plus t star give rise to symmetry because little vectors give rise to closed vector fields, and 1 forms, you can take d of that, becomes a 2 form, and then it kind of fits in this framework here. So you have a whole bunch of symmetries, but the point is that there's more. And this particular symmetry here that you have when B is closed is called the B field transform. It comes from physics. And then it becomes something that becomes a natural thing to consider whenever you're asking if 2 structures are equivalent or not. It's always up to diffeomorphisms and B fields.
And can we think of this B field transform as some sort of like gauge transformation type thing, or how do you think about it physically?
Yeah, so like they like to think of it like that. I don't know if it's more than an analogy, because they say, if it was a 1 form, it was a bit like electromagnetism. It was a connection on a U1 bundle and or something like that. And now it's a 2 form, so it's kind of like that. But I think it's just an analogy. I don't think there is like a concrete gauge group behind it. The correct framework is that this age, one way to think about it is that the 3-form age should be like the curvature of a U1 germ, and then this B is a change of the connection changing the connection on that U1 germ. So something along those lines. So you can think of it a bit in those terms. To me, it was never useful, but it's there. And now that we understand a bit of what t plus t star does, we can actually start looking for generalized complex structures. There are 3 definitions that are equivalent. And the first one is kind of modeled on what a complex structure is. You just pick some, so t plus t star already has some structure, has this pairing and it has this bracket, right? So you would like to have a complex structure in that space. But because I already have this metric, it kind of makes sense to ask that it's compatible with it. So you ask it to be orthogonal with respect to the natural pairing. The other thing you ask is that the plus eigenspace should be involutive with respect to the bracket. So in complex geometry, that's a theorem. If the plus eigenspace is involutive, Newlander-Nirenberg tells you that it comes from complex coordinates. Here we don't have complex coordinates, we don't have the correct notion of coordinates, but it makes sense to say, well, instead of using that as a theorem, use that as the definition of integrability. It's something that happens frequently in other structures as well. So requiring involutivity seems to be a reasonable thing to do when you want to impose integrability on things. The way it happens, a complex structure is fully determined by its plus I eigenspace, because the minus I is just the complex conjugate. And if you have the plus I and the minus I, you can find the whole linear transformation. So you can actually just phrase the whole generalized complex structure in terms of just the plus I eigenspace. It's a subbundle of the complexification of t plus t star, which doesn't intersect the complex conjugate, because the plus I and minus I eigenspace should not intersect. maximize the tropic should have half of the dimension and should be involutive with respect to the bracket. So the first two conditions are pointwise linear algebra, and they're just to say that you get an orthogonal complex structure. And the last one is the same integrability you had before. So this is kind of okay. If you thought a bit of complex vector spaces, that was not particularly bad. The next one is one that kind of can be a little tricky at times. Takes some getting used to, and it's much longer. So generalized complex manifold is this. It's a line subbundle of the space of forms. This line subbundle should be pointwise generated by a form of a very specific algebraic type. So it has to be e to the b plus I omega. So that's a formal exponential. And b plus I omega is just a complex 2 form. Wedged with omega, and this omega is a decomposable form. So it should be something like alpha 1, wedge alpha 2, wedge alpha 3 with this guy's 1 forms. And so it has this algebraic type. And pointwise, you should have this property here for those omegas and these guys that we introduced here. So the b somehow doesn't show up in the equation, it's just the little omega and the big omega. And here the k is the degree of the big omega, and n is the real dimension of the manifold. So this should be a volume form, and saying that this actually is non-zero where it's defined. And that's a really weird condition if you have not seen this kind of thing before. So I think we have to see a few examples to see what happens. But these two are just the pointwise things. The relationship to the thing that I was talking about before is that you can look at the space of all vector plus forms, which when you contract by interior product and wedge with exterior product, that actually kill that form. And that would be precisely the L that we had before, this plus eigenspace. So by having it at this particular algebraic form gives you a maximal isotropic subspace. And this pointwise condition that we have here is the one that ensures that L intersect L bar is trivial. Okay, so this one is maximal isotropic. And the other one is L intersect L bar is 0. And then I mentioned that the bracket is related to this exterior derivative twisted by h, and then integrability, so being involutive, becomes this kind of equation here. So if instead of having just a pointwise guy, you had a local section, a local nor vanishing section, then if you take dh of it, it should happen just like that. It should be, again, like, so to speak, a multiple of it. Here, x is a vector, so it acts on forms by contraction, interior product, and xi is a one form, it acts on rho by exterior product. So x decreases the degree, and xi increases the degree. First time we see this kind of thing here, it looks really weird because it's a multi-degree form. Like the parity of it is well defined because the e b plus I omega is a 2 form, but it really has something in degree, say k, which is the degree of the big omega, k plus 2, k plus 4, etc. So it's kind of weird to think of it, but you can see that even if rho had constant degree, this kind of integrability here involves taking interior product of a vector which decreases the degree and exterior product with one form which increases the degree. So like it would mix up anyway. So it's kind of, it belongs in the world in which you actually just mix up the degrees of forms. So then it's good to have some examples just so we understand a little bit what's going on and what that K was. So if you have an almost complex manifold, you can define this structure there. So you have a complex structure in every tangent space. So you can take the dual structure, you get one also in every cotangent space, and you can put them together. And notice that I have to put a minus here, and that's because it has to stay orthogonal. If I had not put the minus, it would not be orthogonal with respect to the pairing of t plus t star. But once you do that, then you get this plus eigenspace. Because of the minus, it's the minus eigenspace on the tangent space and the plus eigenspace on the cotangent space. And involutivity of this L is the same thing as involutivity of the plus eigenspace of I, which is the same thing as integrability of the complex structure. So an almost complex manifold is actually integrable as a just complex manifold if and only if it's integrable as a complex manifold. And what was that line bundle that you're talking about? It was just the canonical bundle of your complex manifold, so just omega n0. Omega n0 is locally generated by dz1, dz2, etc. It's decomposable, and there's no b plus I omega there. It's just 0, but it satisfies the condition. So if you pick a section of the canonical bundle, it automatically satisfies omega bar is non-zero. It's a volume form everywhere.
And you said you had to put minus I, but you could put I and minus I star, no?
I could have put the minus I star, yes.
Just you made the choice of taking the I eigenspace instead of minus I.
Yes, so like it is purely cosmetic, in the same way that like in complex manifolds, when you're first learning, there's the del and the del bar operator, and there really is no distinction between the two of them. But for some reason, we like to use the del bar operator because del bar is equal to 0 is the holomorphic condition. So this choice is made so that later we have the del bar operator appearing, and you can talk about holomorphic instead of anti-holomorphic objects. But it really could have been the other way around. The other example, which I promised, was symplectic manifolds. If you have a symplectic structure, you can think of the symplectic form, I'll just write it up here, as a map from the tangent bundle to the cotangent bundle, which is an isomorphism. So you can also invert it, so you can go backwards with omega inverse. And then you can make this matrix here. And the idea is that because I want this square to be -1, I put a -1 here. So this -1 is different from the previous one, which was therefore orthogonality. Here, this one is here because I wanted to square to -1 instead of +1. And then you can go and figure out what is the plus I eigenspace. It's given by x minus I omega of x. So it's a vector plus 1/4. For every complexified vector, you get one of those. And this is involutive if and only if d omega is equal to 0. So I already used non-degeneracy up here to be able to talk about omega and omega inverse. And then the integrability forces it to be symplectic as well. So it really is equivalent to being symplectic. And the canonical bundle in this case, the K, is just this multi-degree form here. So e to the I omega. So it's one, and this one is nice because it's globally defined. You have like immediately this global section, different from the complex case, which the canonical bundle may or may not have a global holomorphic section, or even a global section at all. Here, you always have a section that's defining the whole symplectic manifold. And you can act by two forms that I said were symmetries of the structure. So the action by two form just puts a b plus I omega instead of I omega. And what happens from here is that we actually, whenever we see something like this, we understand that, well, this is just a symmetry acting on a symplectic structure. So I'll just call it also symplectic, okay? Instead of say, oh, this is something else. So b plus I omega, for me, is just a symplectic structure with some symmetry that I'll most of the time just ignore in my mind. If I had a holomorphic symplectic manifold, so that means that now omega, so the manifold is complex, and omega is a complex symplectic form. So omega right now is a 2-0 form, which is symplectic on the T10 of the manifold. Then I can, so which means in particular that omega to the n is a section of the canonical bundle, which is nowhere vanishing for the complex structure. So what I can do is just pick the following collection of structures, and here they are phrased in terms of the canonical bundle. I'll have t is just a scalar, it's a parameter. So I put t to the n, omega to the e to the omega divided by t. Just expand the exponential, becomes something like this. And then the question is like, what happens for t non-zero? What happens at t equals to 0? For t non-zero, it is of that form, b plus I omega. So it's symplectic for every t non-zero. When t is equal to 0, you see that all these coefficients here will disappear except for this last term here. This last term remains. So in the end, when t is equal to 0, I'm just looking at the line generated by omega to the n, which is the canonical bundle of the complex structure. So whenever you have a holomorphic symplectic manifold, you can actually deform from symplectic to complex in a continuous family of integrable structures. Okay, so this is like the bizarre thing that I think the first time you see it's funny. You get used to it over time. But that's like, so they really live in the same world, and it's not like in the Isotropic that you never have a Lagrangian that will deform and suddenly become the whole space and symplectic, right? So this is like they are connected. It's not that there's a grading and you're always in one of these and there's no communication between them. And here is the other interesting thing, which is that you can consider, and here I'm just going with the canonical bundle again. You can consider the line generated by this form here, z plus the z wedge dw. So this is a funny one. So there are a couple of pointwise conditions. So first, the condition that omega bar, so that one can, the thing that should be non-zero, the volume form should be non-zero, that you can check, and eventually it always boils down to the fact that the z dw wedge, the z bar, the w bar is non-zero on C2. More relevant, I'd like to check that pointwise it has the correct algebraic form, and if z is non-zero, it becomes this exponential here. So it's a non-degenerate 2 form if z is non-zero. So it's again like this B-field transform of symplectic. It's symplectic type. When z is equal to 0, this leading term disappears. This term here will disappear, and you just get dz wedge dw, which is complex. Like that's precisely how the complex structure comes about. This is a section of the canonical bundle of the complex structure. So you see that this structure on C2 is symplectic at some points and complex at z equals to 0. So you can actually move from one to the other. It's not that sometimes the manifold is fully complex and sometimes fully symplectic, and you can connect them. Sometimes within a manifold, you can actually go from complex to symplectic in a smooth way. So this is a well-defined structure. So it's symplectic for z non-zero and complex for z equals to 0. And of course, it's in C2, it is very non-compact. You could say, well, can we get a compact example? And at the moment, not quite yet. But you can take quotients by translation in z in the w direction, because the way the w appears is clearly invariant per translations. So I can at least make the locus where it's complex, instead of being a whole copy of C, I can make it into a copy of the torus. So the complex locus can become compact in the example, but the rest of it is big open manifolds for now. And that kind of, this example illustrates a bit things that we'd like to understand, because this really shows like there's an interesting feature here that doesn't exist in just complex or symplectic world and seems to be quite relevant. So that kind of brings our attention. Like this seems to be important. We'd like to understand better the geometry of the type change locus, this place where it goes from symplectic to complex, or the place where it becomes different, where it doesn't have homogeneous behavior anymore. And I would like to understand also the new features that you get once you do this. So which new features you get on these giant complex manifolds that were not there before. So let me give you a couple more examples, because you can just think for a second, like before I had put just z plus zdw, and what did I really use about z there? I kind of just used that it was holomorphic. Maybe I even forgot to do the computation. I think I just forgot to tell you, this is the computation for integrability. I think I skipped it. When you take d of it, it's just the second term doesn't have a d, so you just get dz, and dz is really ddu applied to the thing where w is equal to u plus iv. So if you just take interior product with ddu has to jump the dz, contracts with the du from the w, and then it gives you a 1. So if you do minus the du, this contraction just becomes dz. So you get the integrability with a non-zero term there. So in this case, it's a vector giving the integrability. So what did I use going forward? What did I use to do this computation? It essentially was the fact that z is a holomorphic function. So that's I can actually realize dz as a contraction of something on this dz dw. And if I had put pretty much any holomorphic function there, I'll get another example of something with type change, which is complex where f vanishes and symplectic elsewhere. So like I can produce many local examples of this kind of thing. And then you can say, well, what about if I was in higher dimensions? Is it as simple? Well, in C3, I have a few examples appearing here. So I can consider like alpha 1,0 form plus dz1, z2, dz3. And as long as alpha is holomorphic, so del bar of alpha is equal to 0, this is always going to be a Transcomplex structure. I'll always satisfy the integrability conditions as well. But here there is something that happens that's more interesting, because before it was always vanishing along the 0 of a holomorphic function, so it's codimension 2 condition. And here the question, like, where does it behave differently? And in this first example, I have z1 dz1 plus this complex volume element. So that one has a problem in z1 equal to 0, so it's a hyperplane. Here I have another example with z1 plus z1 plus z2 dz2, and that vanishes only if both of the one forms vanish. So it's a line, z1 equals to 0 and z2 equals to 0. In the third example, you have z1, z1, z2, z2, z3, z3. So for that to vanish, it's only if you are at the origin. So you can actually have the type change when you start going higher in degree. It can happen not just in codimension 2, but also in lower codimension. And it remains a question, like, what is the geometry of this type change locus? That's something I'd like to understand. It's something that bugs the physicists, because they would like to use these structures, but they come with this type change locus and they don't have a way to deal with it. So They can only do things if it involves, like, I can integrate, because I know it happens in coordination 2 or higher, so if integration is fine. So if I have a Keller potential or something, that probably works fine, but like I lose Stokes, and I lose some other interesting features. That's just because I kind of remove the place where things go bad. So just to give an idea, so those are like local examples, but you have actually a collection of examples that happen in compact manifolds as well. So you can actually use those toy models to kind of glue them into compact manifolds. And here we have a collection of them. So if you look at all these families here, so here's connected sums of an odd number of CP2s and any number of CP2 bars, that always has a giant complex structure. Sums of an odd number of S2s cross S2s, that also has a giant complex structure. And you can have sums of a certain number of S1s cross S3s, CP2s plus CP2 bars. And the condition, or S2 cross S2, and the conditions that we get here are two. One of them is that the sum L plus N should be odd, and that is just because you need an almost complex structure for this work. So if it's even, you actually can prove that these manifolds would not admit giant complex structure for topological reasons. The other condition, which has to do with how we create these things, is that the Euler characteristic has to be non-negative. And this is, as far as I can tell, is down to the way we construct it. So somehow we construct by putting contributions to the Euler characteristic in our construction. So it's always like non-zero positive contributions. It's not clear to me at the moment if this is something inherent, that you cannot produce examples with negative Euler characteristic. And this would be of a specific type stable, because you do have examples of negative Euler characteristic which are not stable. So the second condition here, that a positive Euler characteristic, they seem to be a feature of the construction, how these spaces were obtained, instead of a giant complex thing on itself, but we do not know. And it's also worth mentioning that of all these manifolds we have there, only when n is equal to 0, in all these cases, no, in the top two cases, only when n is equal to 0, and in the bottom cases, you can either have n equals to 0 or n equals to 0, L equals to 1, or the other way around. These are the only ones that actually admit complex or symplectic structures. So most of the spaces are not complex or symplectic. We know that for sure, and they're all giant complex. And one thing that we may or may not know is that connected sum is not a good operation. So even though they are like nice manifolds, all with connected sums, remove a disk here, remove a disk there, glue them together. This is a bad operation when it goes to symplectic geometry or complex geometry. So that's why, even though they all look nice and pretty, none of them is complex or symplectic. So the kind of open questions we get are all almost complex form manifolds giant complex. So all those lists, there was a coincidence, and it's weird that there was such a coincidence. Another question similar is, do all stable giant complex form manifolds have non-negative Euler characteristic? And here the word stable is important, because if it was not stable, we have examples. They're easy to construct, actually. So it might be a feature of the construction of those particular manifolds. And a different one, which is that in some cases the form is closed, in some cases you actually need this x plus psi. And then is there a type changing giant complex structure which is actually defined by closed form? So we had one example here. Sorry, let me go back. All these examples here, they are defined by closed forms, but they are on C3. So the question is, can you do that also in a compact manifold? And that has been eluding us all these years.
Gil,
yes.
Can you remind me? I don't remember. I might have asked you. S6.
S6.
What do you know about S6?
We know nothing. You know it's round. We do not know if it has, if you could prove, like, even though that's not the question that people ask, if you could prove it has a giant complex structure, I would already be super happy.
Okay, so now what would, like, towards proving that S6 has a complex structure, you can think as proving that there's a generalized complex as intermediate step.
That's right, yes.
What would be the difficult part? To prove that there's a generalized complex, or turn generalized complex into a complex?
It's very unclear to me, what I just argued that in 4 dimensions, there was a coincidence in large families, there's a coincidence between having generalized complex and just being almost complex. So based on that, it might seem that S6 has a good chance of being generalized complex, much better chance than being just complex, right? But even that is very unclear, like how you go about doing that. At least it's unclear to me at the moment. We have all sorts of surgery and so on, but S6 is difficult to, like, it's very simple. When you do surgeries, you have topology. That's all missing there. So now I'd like to talk about deformation. So that's kind of going towards the part in which I tell you about the relation to holomorphic Poisson structures. So let's just see here, how do we set up the deformation problem? So instead of looking at T plus T star, which normally we like to describe it like this, T and T star, now we have these other two spaces there. So I'll put the complexification here. We have these other two spaces there, namely the plus I and the minus I eigenspace. So I have these other two guys here, L and L bar. And they also give me the whole space. So instead of thinking of T plus T star as the sum of those two guys, I think of it as the sum of L plus L bar instead. So from now on, it always looks like this, L and L bar. Okay. And then the way to deform this structure, since L determines the generalized complex structure fully, would be to just try to pick another maximal isotropic subspace nearby and check if it's integrable. So there are two steps here. One is just describe the nearby ones. That's pure linear algebra. It's simple. And in fact, to keep it isotropic, so the idea is that the natural pairing makes L bar isomorphic to L star, so the dual space. To do this trick here, you just need to get the graph of a map from L to L star or L bar. So just need something in tensor 2. And to keep it isotropic, you need it to actually be skew symmetric. So that was a bit quick, but you just need an element in wedge 2 of L bar or wedge 2 of L star, and that gives you an isotropic element. Because L didn't intersect L bar, if you just move it a little bit, it will still not intersect its complex conjugate. So you're all good there. And the only question is, what about integrability? Okay. And then here you have the integrability theorem. I do say Gualtieri, but technically, probably it's Weinstein-Schuh, and like it's the kind of thing that had appeared before, but not with the word Transcomplex included in it. So it was in the context of Lie bialgebroids. But that's the situation. If you have an element in wedge 2 of L star, so section technically, so I forgot to put the section symbol here. So if you have a section on your whole manifold, and you look at this new space here, which is the one I was just describing now, this space is going to be involutive if epsilon satisfies this equation here. And I'm not going to be talking too much about it. So essentially L induces a differential operator on L star. And because the whole situation, there's a natural bracket in sections of wedge 2 of L star, and so also you can pair everything together and get an equation like that. So there is like a very concrete differential equation that tells you if something is integrable. So there is a very concrete way in which you can transport the question of integrability into different PDEs, geometric PDEs. If you are complex, you might feel that you are in a better situation because the tangents, the L or the L bar, here I'm using L bar, actually decomposes as a sum of two guys. Decomposes a sum of two guys. So in principle, you can write more equations just by decomposing the equation I wrote before into its components. So wedge 2 has 3 terms, which is like a 2 form, so something bivector, so something that lies in here, and now, yes, something that lies here in the middle, so it's in the wedge of these two guys, and a 0-2 form. So I call them epsilon 1, epsilon 2, epsilon 3 respectively. So epsilon 1 is a bivector, 2 is some sort of endomorphism, and 3 is a 2 form. And I can write the same equation, but now I know I'm at a complex point, so the DL becomes just the del bar operator that connects with Marius's question. The bracket is a bracket like extension of the Theorem bracket on forms, but it's also an extension of just the Lie bracket. And becomes these 4 equations here. So you get 4 different terms because the wedge 3 has like 4 terms. Like wedge 1 has 2, wedge 2 has 3, and wedge 3 has 4. You get 4 equations. If they're all 0, you got something integrable. And you see that these terms, even though I had 1, 2, 3, they kind of, in integrability, they mix up a lot. So the first one just involves 1, but the second equation already involves 1 and 2, and the third involves 1, 2, and 3. So it becomes difficult to kind of say something when you just look at all that. So the first step, say, well, what if we put a whole bunch of these guys to be 0? So for example, what if epsilon 1 and epsilon 2 were both 0? What if epsilon 1 and epsilon 2 are both 0? Then you see here that this first term here is going to disappear. The second term has epsilon 1 in both of it, disappears. The third one has epsilon 2, epsilon 1, epsilon disappears. The third one has an epsilon 2 here, so this one disappears. So you're just left with this condition here. Well, much better. So that one I understand is just saying epsilon 3 is some sort of 2 forms, a complex 2 form, and you can use it to deform your complex structure, and you get something integrable. Because you already saw 2 forms are good for deformations. Just kind of shift the t into the t star part, right? And it's integrable as long as it's holomorphic type of thing. It's a 0-2 form, so it's not really, doesn't make sense to call holomorphic, but it's del bar equals to 0. So okay, so that was an easy one. So this is deformation by 2 forms that we kind of had seen early on related to the symmetries. Okay, so case 2, what if epsilon 1 and epsilon 3 are 0? So this is the bivector and the 2 form, and I'm just left with the endomorphism. So again, this term here, I see it goes away because it has epsilon 1. Here it has epsilon 1 in both, so it goes away. This one here has epsilon 2, this stay, but this guy disappears. And here has epsilon 3 on both, so it also goes away. So what you're left with is just that. There's a single equation again, and that's precisely the type of equation you get when you want to deform a complex structure as a complex structure. So that's when does an automorphism of the tangent space give rise to an integrable deformation of a complex structure. So this is something from the 50s. It's just genuine deformations of the complex structure. Okay. And the third one is when epsilon 2 and epsilon 3 are both 0. So now I'm left with epsilon 1. So here, this term here stays because it has epsilon 1. This one here simplifies a little, but the second one disappears, the first one does not. And the rest of it always involves epsilon 2 or epsilon 3, so they all disappear as well. So the equation becomes 2. The first one is the Poisson condition for that bivector. And the second one is say that the bivector is holomorphic. So if you have a complex manifold and you have a holomorphic Poisson bivector, you can use that holomorphic Poisson bivector to deform your complex structure into something which is no longer complex. It will become generalized complex. So that's a clear relation between Poisson geometry, holomorphic Poisson geometry, and generalized complex structure. So holomorphic Poisson geometry existed before anyway, but you see that holomorphic Poisson is precisely the condition that you need to use a bivector to deform a complex structure. So you can go back to the examples I had before, and the holomorphic symplectic example, for example, was the same thing as a non-degenerate holomorphic Poisson structure, and that was the one that interpolated between complex and symplectic. On C2, the example that I gave with Z plus the ZW corresponds to using this holomorphic Poisson bivector here. And the other one that I had, for example, this one of cyclic permutations, was the one that gave me this particular structure. So all the examples I gave before, they're actually all holomorphic Poisson examples. So there is a rich holomorphic connection to holomorphic Poisson geometry on this thing here. And now that we have this holomorphic Poisson picture, one thing that comes is that you can actually consider compact examples. Before I claimed that some examples were examples of generalized complex manifolds, but now I can actually argue that that's the case. Because if you pick any surface, any complex surface, any holomorphic bivector is automatically Poisson, because the wedge, like the bracket of itself, would be in degree 3, which is too high for the dimension of the space. So in complex surfaces, all I need to do is to look for holomorphic bivectors. And then you look at them, and funnels have plenty of them, among other manifolds. But funnels are like a rich source of examples of holomorphic bivectors. Examples of funnels, if you don't know what they are, CP2 is one, and S2 cross S2 is another. Okay? And there's a third one, which is not a funnel, but also has a holomorphic Poisson bivector, which is primary Hopf surfaces. So suddenly you can actually put generalized complex structures on the spaces. And one of the features is that here, the holomorphic Poisson bivector will vanish at some points. So the points where it vanishes are points where you're not deforming, because you're using that to deform the structure. So where it's 0, you don't move. So points where the Poisson bivector vanishes remain complex, and the other points become symplectic. So CP2 will have a generalized complex structure, which is complex along a cubic curve, and is symplectic elsewhere. And just to continue, because of course, like it seems that I did all the analysis that I could possibly do, right? Like I let each pair vanish, and kind of saw what I'll get out of that. There's one other case that's worth considering. It's when epsilon 3 vanishes. So that is the two-form part, epsilon 3. So what happens if epsilon 3 vanishes? I'll start removing the terms of epsilon 3. So this one here disappears, and this one also. The last equation goes away. This equation here, this middle term disappears, and that's it. So like I'm left with a whole bunch of things. So let me look again. This is what I'm left with. Now I have to remember a little bit what happened before. This equation here is the one that says that epsilon 2 alone gives me an integrable deformation of the complex structure. It's the same one that I had before when epsilon 1 was 0, like epsilon 1 doesn't appear there. So even though I have epsilon 1 and epsilon 2 alone already gives me an integrable deformation. This equation here doesn't involve epsilon 2, it's just saying epsilon 1 is a Poisson bivector. And this condition here is to say that epsilon 1 is holomorphic for the deformed structure. So if I was to look at the reference structure where I start, epsilon 1 is just whatever, but I can use epsilon 2 to get a new integrable structure. And for this new integrable structure, epsilon 1 is actually a holomorphic Poisson deformation. So in a way I can describe this particular deformation given by epsilon 1 and epsilon 2 as a two-step thing. First I deform by epsilon 2, get an integrable complex structure, and then I do a holomorphic Poisson deformation from there. So that's the conclusions. First complex plus a holomorphic Poisson deformation. So I would just like to tell you like what the results are for this. I'm not going to prove anything, but the idea now is essentially this: like if there's no epsilon 3, so that's how we tackle this kind of thing. If I could somehow do my deformation so that there was no epsilon 3, then I know it's a holomorphic Poisson deformation of a complex structure. But if you give me a deformation in principle, it has all the three components. But I always have this action of the symmetry group, the diffeomorphism and the two forms. So what I can do is say, well, I can try to kill that epsilon 3 by a symmetry. So instead of, if you give me a deformation, instead of using that one that you gave me, I'll try to gauge the epsilon 3 away so that I get a deformation that only has epsilon 1 and epsilon 2. And once I have that, I can automatically conclude that it's a holomorphic Poisson deformation of a complex structure, not necessarily the one I started with. And that's weird, because like S2 cross S2 can have many complex structures, and the first thing is like some other, like it's not the one you thought. Anyway, so that's the approach. We kind of gauge away this complex structure. So like the first theorem, it's a global form theorem, so to speak. I don't know if I should call it global form, but it's a global theorem. If I have a compact holomorphic Poisson manifold, and if I have that this map from H2 to H02 is surjective, as you'd have, for example, if your manifold was keller, then all the nearby generalized complex structures are B-field equivalent to holomorphic Poisson structures. So that if I mean in a manifold, in a complex manifold where this map is surjective, I can only deform in holomorphic Poisson directions. So everything is always in this realm of holomorphic Poisson. Do not get something new from generalized complex. And as I was saying, part of the idea is to gauge away the epsilon 3, use the symmetries to kill that part. So we set up the whole thing. It's already a PD, so it's a clear problem now, like a clear analytic problem. So you can use analytic tools. And the tools are like we transform everything to Sobolev space. So the first thing you do is kind of remove this smoothness of all the objects involved. Then you have, if you set it correctly, you can use the implicit function theorem to conclude there is a solution, but then the solution is not smooth. And then you have to look at the operators you have and use elliptic regularity to conclude that, in fact, because it's a kernel of some nonlinear elliptic operator, you are actually smooth. And like when I was looking at this, it already kind of seemed to be pushing, because in my mind, like I'm not knowing much PDEs, I thought to know if you are a solution to an elliptic, nonlinear elliptic PDE with smooth coefficients, you surely should be smooth because the word elliptic is there. And like, what's the point of having the word there if it doesn't give you regularity, right? Then you start looking for that kind of result, and it's not there. I don't think it's known or true. I don't know. Like I couldn't find it. And then there are a few examples. So they do have a few results for nonlinear PDEs, but they cannot just do the full nonlinear elliptic PDE. For our luck is that it was just at the limits. There are elliptic PDEs that are called of divergence type. So for up to that point, nonlinear elliptic PDEs of divergence type, you can actually get regularity, and that kind of result that you can get from the book already is enough to get this theorem. but it's like there is some analysis that goes into here, and some what to me seems like a bit obscure, but it's elliptic regularity for some hard-ass elliptic operators. So going back to the examples we had there, so like if you pick small deformations of CP2, CP2 is complex, and in fact that map from H2 to H02 is surjective. So for CP2, it is the case that all the nearby deformations from the complex structure will be of holomorphic Poisson type. So there's nothing else around the symplectic structure but just holomorphic geometry. Same thing for S2 cross S2, and like I wrote there S1 cross S3, but actually I should check. S1 cross S3, of course, has no degree 2 cohomology, but I also think it doesn't have 0-2 cohomology either. So it's just like 0 and 0. And now we have actual local form theorem. So that one was a global one. And the first local form theorem is one that came quite early on and doesn't say much. It's just a direct translation of Einstein's splitting theorem to generalized complex world, which is to say that if you have a generalized complex manifold and you pick a point, in a neighborhood of that point, your structure is equivalent to something which is purely symplectic, so the symplectic leaves, times a transverse structure which is of complex type at that point. But it doesn't really say, like, so this J here, all we know about it is that it's complex at the origin. We do not know at this stage that it's holomorphic Poisson or anything, and it C is non-compact. The previous result, I needed compact manifolds. And you can imagine that if you have done a little bit of analysis, you know that non-compact is bad. So like trying to translate that into something decent would require some tools, and that's what Michael Bailey did in his thesis. Michael Bailey was here for a few years. If you have a generalized complex structure which is complex at a point, then it's holomorphic Poisson in the neighborhood of that point. So this is like a deep result for people who have done the project in complex manifolds orientation. One consequence of this is Nylander-Nirenberg. So you can just think like one example of generalized complex structure in a neighborhood of 0 is just a complex type 1, an integral complex type 1, and the result he has is that equivalent to the one on CN. So what he proved there was like a stronger version than a stronger theorem than Nylander-Nirenberg theorem, which normally just say, oh, it's difficult, and then we don't look at it. So that was one.
Is there still a hope to prove this using Nylander?
Yeah. So like the next one. So like it's just that the way he used both. Like he did not use the strategy that I was just talking about. He used diffeomorphisms and one forms to bring it to the standard structure. And the way I was proposing, you just use one form. You don't just use the epsilon 3 to gauge away that last component. You just use one form to gauge away the epsilon 3 component. And then the conclusion is just that you are a Poisson deformation of a complex structure on that same space. But then you can say, well, Nylander-Nirenberg tells you that in the neighborhood of a point, it's always complex. So like this new approach, you can kind of use Nylander-Nirenberg instead of having proved it.
Does it work? Or is it?
It does, yes. We argued it in our paper. But like with that said, it remains a complicated argument. So it remains a complicated argument. So it's like it's not as if we suddenly could, oh, look how easy it is to prove this one because it had Nylander-Nirenberg. And this is the result that I just wanted to mention. And this one is a kind of a difficult one to parse because it has all sorts of words that I did not define. And it's good as the last slide, so it's all good, right? So like if you didn't understand that one, you understood everything that came before that. So look at how many bullets that was. Wow. So the point is that I would like to say, find something that behaves holomorphically in a generalized complex manifold. And there are many things that do not, because if you think symplectic manifolds are examples, symplectic manifolds are examples. So there are many things which are not holomorphic. So the idea is like, what kind of object is there that induces local holomorphic data? So say holomorphic data on the subspace and on the normal directions, for example, the normal bundle. So that's what we kind of dug up. So there are a few conditions that you have to impose. One of them is that it's a brane. Brane is the generalization of complex submanifold for the whole generalized complex world. It has to be a Poisson brane, so it has to contain its symplectic leaves. And abelian is something that's about the behavior of the generalized complex structure in normal directions. And I guess the point of all this is that brane is about what's going on along the manifold, and so is Poisson. And abelian is first order information in normal directions. So this is really infinitesimal data that I'm asking here. If I have one such a thing, which is full of words that we didn't really describe, but I try to argue that it's all, let's say, infinitesimal information, then because of that, that's the kind of the important point. Because of that data, I actually get to produce a complex structure in this space, which may or may not be related to the original one. It's just that this data contains enough information that a holomorphic structure appears on the submanifold and on the normal bundle. So technically, there's a tubular neighborhood which admits a complex structure that I could cook up out of the data from the generalized complex structure. So at least like infinitesimal data only. So at least there is some hope that there will be a relation between these two. It's not just something that I put there by hand, but something that I extracted from the generalized complex structure. And once you have that, again, you have something similar. So if there's no cohomology here in a tubular neighborhood of that space, then there exists an exactitude form, and J is B-field equivalent. So J is holomorphic Poisson. That's kind of the message here. Or gauge equivalent holomorphic Poisson. So part of it is like get these brains, get the correct manifold which induces the correct holomorphic data, so you can compare it to something that makes sense compared to. And there is a condition on vanishing of cohomology, plus like 2 and 3 convexity. And this is again something that we need to, part of the proof, we need to do this whole elliptic operator theory. And to do that, to get elliptic regularity and so on, when you have a complex manifold boundary, the shape of the boundary, how convex or how concave it is actually important. It's not like in real geometry, which that doesn't come up. So there's some condition of it being convex or concave enough that you can actually do Hodge theory in the degrees that you're interested in. But then you conclude that is a large class of families that is of holomorphic Poisson type. So this was the theorem, and this is kind of where I stop. And apparently it's all good because it's 5 o'clock according to that clock, which I have no idea if it's correct, but I have been using. Oh yeah, look at that. And I'll just like to mention that this kind of result allows us, for example, to do like blow-ups you already knew how to do, but now you can also do blow-downs, which is kind of way harder because to do a blow-down in a complex world, you need somehow like a normal form for a complex submanifold, and that's in rare cases you have. So that's something that we managed to get out of this as well. Yeah, thanks for your attention.
Are there questions?
Just definition.
Right.
It didn't look symmetric, anti-symmetric.
No, it's not. It's not.
Why is that good?
Or
why is it not bad? That sounds like this.
So like you can just skew symmetrize it, and originally it was proposed as a skew symmetric bracket, but originally it was just written down. It's not as if like, oh, we thought a whole bunch, like somehow it was something that people wrote down and just was a skew symmetric version, and you can actually work with just that skew symmetric version pretty much just as well, except that this version, like the bracket acts more like symmetry, it's more like Lie derivative. If you think of Lie derivative of vectors, like the Lie derivative of y in the direction of x for vectors, when I say it like that, it's not a skew symmetric operation. It is the Lie bracket, and it turns out to be skew symmetric, but the fact that if I take the derivative of the vector field y in the direction of the vector field x, is that all related to the other way around? It's not an obvious thing, right? Like, so that's what's going on there. So like in this case, it really is a Lie derivative. So when I do this,
but also on isotropic L, the bracket becomes symmetric.
That's right. So yeah. So like this particular expression, you should think of it as the derivative of y plus eta in the direction of x plus psi, and it's just not a symmetric operation. And pretty much all the time when you do geometry on T plus T star, we look into isotropic spaces. And whenever you restrict yourself to isotropic spaces, the differences appear, because the difference between the skew symmetrization and this guy has just to do with the derivative of the pairing of the sections that you're using. So like if you skew symmetrize, what you kind of add or subtract is like half of the derivative of the pairing of x plus psi on y plus eta. So if it's skew symmetric, it doesn't really matter. So the notion of integrability would not change if you had used the skew symmetrization. but this one is like the lead derivative, and because having like here it didn't make a difference, but we in our context we're doing deformations, and you also would like to consider when two deformations are equivalent, so you kind of need to know the flow of the symmetries, and then this one just is more natural.